turning on our camera throughout the class today because I just thought that during Ramadan, if you want to increase your barakah, then in a class normally I could see my students, yeah. So why not we try that? Yeah, I've given you chances for the last 5 weeks for you to try on with your camera thing, unless if you still have other problems which you haven't tried to solve very hard that technical problem for the last 3 semesters, and we are on the first day of our PKP today in Selangor. So think about it, yeah. Think twice, thrice, as many times as you should think. You need this ODL thing, and it's going to be virtual for quite some time. Yeah, we thought that it's going to finish in a year or so, maybe less than a year, but no, it's not. Yeah, so we're going to do it seriously and for Barakah Ramadan. Why not? All right. Now, so we'll start our class with dua. You know the drill. You know the drill.
My voice clear?
Tapi semua dah buka kamera ke?
Oops. Okay, I'll start the dua then. أعوذ بالله السميع العليم من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين حمدا يوافي نعمه ويكافئ مزيدا يا ربنا لك الحمد كما ينبغي لجلال وجهك الكريم وعظيم سلطانك اللهم صل وسلم على سيدنا محمد وعلى آله وصحبه أجمعين اللهم اغفر لنا ذنوبنا ولوالدينا وارحمهما كما ربيانا صغيرا اللهم
اللهم اجعلني في قلبي نورا وفي
وفي
لساني نورا وفي
وفي
بصري نورا
بصري
وفي سمعي نورا
نورا
وعن
وعن
يميني
يمينه
نورا وعن
وعن
يساري نورا ومن
ومن
فوقي نورا
فوق
ومن تحتي نورا
وتحت
ومن أمامي نورا ومن خلفي نورا واجعل لي في
وجعل
نفسي
في
نورا.
نفسي رب اشرح لي صدري ويسر لي أمري واحلل
واحلل
عقدة من
عقدة من لساني
لساني
يفقه
يفقهوا
قولي.
اللهم افتح
اللهم افتح علينا حكمتك وانشر علينا من
من
خزائن رحمتك يا
رحمتك
أرحم
أرحم
الراحمين.
الراحمين سبحان ربك رب العزة عما يصفون وسلام على المرسلين والحمد لله رب العالمين آمين.
Amin, amin ya rabbal alamin. Thank you to Mr. Akasha. Moga-moga segala doamu dimakbulkan di 10 Ramadan yang terakhir ya. Moga-moga semua doa kita juga dimakbulkan di 10 Ramadan terakhir ini. Alright, thank you so much. So, as you read from my agenda, just keep turning on your camera because I want to see you. Trisha, Hanani, Ezwan, Fazlin, Afsa, Najwa, Amira, Umaira, Mashita, Shafika, Azian, Camelia. For the rest who have not opened your turn on your camera, please do so because I want to see you while I'm teaching, whether you could understand what I'm teaching or not by your expression of your faces. Yeah. Dalam kelas selalu saya boleh nampak muka dan boleh je saya ada soalan something like that, yeah. So mind me if I keep looking at my side because I will look at my second screen to look at your faces, yeah. But when I'm looking at my screen writing it, then the camera will see me up front, yeah. All right, so we will start with the class now. I will share my slide. Right. I hope you can already see my slide. I will go straight away to the last slide that we have covered for your class EH2204K, and I think we stopped. Here, yeah? If you have your notes, maybe you have your scribble on it, and you may remember where I stopped my slide, but I save it so I know that I stopped here. But anyway, before I proceed, so this is a part 2, plug flow reactor, PFR for a single and series and parallel. So we are going to look into the comparisons between single, series and parallel. I'm going to make it very fast, because we're going to finish part 2 and part 3 today, and the second part of the lecture today. After that, I will show you one of the exercise. I will give you some time for you to scribble your answers on. Then we will have Kahoot on that question. Yeah, so tengok siapa yang jawab betul. Yeah, but it's very easy. My opinion about this topic is totally easy. If you understand it correctly, it should be at your fingertips. And kalau you still feel masih lagi susah dan lambat, susah nak fokus, so there's something wrong with something else. Yeah, most probably you have to practice listening to English maybe, or you have to practice listening to fast communications, or maybe you have to practice practice what? Practice reading a lot more in English, because the engineering questions is very straightforward for topic 5. All right, so we will proceed. So this is a PFR. As you know, to determine the volume of the PFR, we will use the integral form, and therefore having that plot of dx versus the initial molar flow rate to the reaction rate will give you an ascending trend, yeah, whereby in the plug flow reactor there will be change in the x and also the volume. Yeah, to determine the volume simply by the understanding of the integral form mathematically, you can decide the area under the curve. Yeah, so this is what we're going to do. And now we are going to compare it with, let's say if we have two series of PFR, PFR number 1, PFR number 2, you have initial flow rate 0, then FA1 coming out from the reactor 1, then it enters reactor 2, then FA here is FA, you can write it as FA2, yeah, so this is a little bit of typo there, FA2 coming out from reactor 2. So we have two integral forms, so if you use the same plot by the variation of the x, the conversion, then if you say the x here, yeah, the x here for the first plug flow reactor is achieved at 40%. Then after the second plug flow reactor, then it will increase to 80%. Yeah, so we have 0.4, 0.8. So to determine the volume, the total volume of the PFR1 and PFR2 is simply the addition of the sorry, hold on. Lebih tekan sikit je dia jadi gini, sorry ya. The addition of the volume 1 and volume 2, yeah. So the volume under the curve for PFR1 is the blue shaded area, and the volume under the area, sorry, not volume, area under the curve for reactor 1 is the shaded area, blue shaded area, and the area under the curve, which is the green shaded area, is the volume for PFR number 2, yeah. So we have here from 0 to 0.4 and 0.4 to 0.8. Now, so here to speed up, you can read from your Fogler 4th edition, example 2.6. The calculated area under the curve would give you the first volume 0.551. The second volume is 1.614 meter cube. Yeah. So you can see that the volume 1 is lesser than the volume 2. Yeah. So you see that if you start with the conversion 0.4 to 0.8, then it needs more volume, yeah, in comparison to 0 to 0.4. So now you can say that if you compare between a single PFR in comparison to series PFR, the total volume as calculated is the same. So let us go back to our, I think, did we do that before? It is not shown here, but yeah, the single one will give you the same volume, yeah, which is on this slide 67. So the calculated volume for a single PFR is the same as the two series PFR, yeah. In comparison to our CSTR in series, if you go back to our previous slide, not sure which number, but I'm gonna scroll back. All right, this one, page 47, the single CSTR volume is way higher than the series CSTR volume, yeah? So you can try this from example 2.2 and example 2.3 for CSTR. All right, Afsar, okay? Shafika, okay? Nada, okay, no nada.
Okay, then.
All right, thank you. So we are going to go forward to the last slide, which I touched. This one, yeah? All right, so we're gonna now go into PFR in series in writing the formula, yeah? So basically, I started with showing you the calculated volume based on the area under the curve, all right? So here I go into detail how do we do that? Yeah, we normally start with the formula, which you have done this for the last few weeks before, the derivation of formula, and you know that the volume is simply the integral form. Yeah, so this is just an illustration of the inlet with the x naught, then the outlet, the green shaded x1, then the x1 becomes the inlet now. So I purposely changed the color of the inlet and outlet to make it more clearer. Yeah. So we have X2 there as the outlet from reactor number 2, then becomes the inlet for reactor number 3. So you have those series of formulas for respective reactors, yeah, in series, reactor 1, 2, 3. All right. This slide 70 is just summarizing the formula that you have for the series. For example, here we start with x0 to, okay, x3, that would be the overall. It's simply the addition of the integral form for first reactor from x0 to x1, then from x1 to x2, then from x2 to x3, okay? So please do understand how you write the integral form in series respectively. So now we're going to look into what about if we have both combination, the PFR and CSTR. Yeah, now we're going to look into what about if we have two CSTR and one PFR for an isothermal condition. All right. So this is what you see on your slide 72. You have reactor number 1 SCSTR, reactor number 2 SCSTR as well, and reactor number 3 SPFR. So one of the examples that you could see here is in figure 2.9, whereby you see that we have two CSTR there, and on the right hand side is simply the PFR. Yeah. So this is how the PFR are arranged. So according to the how much volume that you need to achieve to that specific conversion, yeah. So it may start with the reactor number 1, then it enters reactor number 2, and then it continues to PFR in reactor number 3. So this is done for dimesyl G and organometallic catalyst unit. It's a dimerization of propylene into isohexanes. And another example that you can also refer to the application of combination of CSER and PFR is propylene to produce isohexanes. Yeah. So this is what you see as an engineer. You know that you're gonna design two CSER with the PFR. Now you need to know what would be the size of both the CSER and also the PFR. Yeah. So we know that we have learned earlier the basic formula for CSER is the initial flow rate that you have with the initial conversion, which is 0. Yeah, over the rate of reaction inside the reactor number 1. Then if you need to achieve certain conversion for the first reactor, then you multiply it with the X1 for reactor number 1. The same goes to, so we have FA not entering, then FA1 leaving. Then the FA1 is now the entering inlet for the volume reactor number 2 for V2 and the targeted conversion X2 for the reactor number 2. And you have the outlet as FA2 with the targeted X2. So therefore, this is where the formula of series principle is used for the volume calculation. Yeah. So we have FA naught. FA naught still knowing FA naught divides by the rate of reaction in the reactor number 2. Yeah, in reactor number 2 times the outlet targeted conversion minus the inlet targeted, the inlet conversion achieved from the first reactor. Yeah, so it means X2 minus X1. All right. Okay. Now, so the FA2 now, so this is FA2. Did I write FA? Sebab saya dah scribble, nampak FA not, but it's actually FA2 now becomes the inlet flow rate for the PFR. And the outlet is FA3. The inlet is X2, the outlet is X3. So skipping all that because you have done that so many times already. So that will be the volume formula for PFR. Simply the integral form between FA naught still, FA naught over the minus RA for the PFR times the dx. Take note, so how do you describe this integral form? You know that we depend on the FA naught, yeah? We depend on the FA naught because FA naught is the molar flow rate that is initially fed to the first reactor. As it continues to the second reactor, to the third reactor, definitely the concentration of A decreases, yeah? So that is why we refer to FA naught. Then minus RA is simply that you know in the PFR, the rate of the reaction along the volume varies together with the V's. So if you don't remember that, so take note, flick back your lecture notes before on the PFR. What are the principles applied for PFR? We know that axially the R changes and also the V. All right. So that is why we have the integration, yeah, and also the X will increase as well. Yeah. So we integrate based on the change of the conversion because we want to know, we want to target for a certain conversion. Yeah. All right. Now, so this slide number 74 showing you as usual with the varying X and also the FA naught and the rate of reaction. We get an ascending trend of the curve. Yeah. So for the first reactor, if you target it to X1, then that's the point where the X1 is. And since this is CSCR, you know that the determination of the area of the X times the Y would represent the volume for the first reactor, yeah, which is CSCR. Since the second reactor is CSCR, you do the same thing, the X times the Y. So how do you determine it? Since you choose this one as X targeted, X2 for reactor number 2. So at that point, will give you the Y value, yeah. And now the third reactor is PFR. Since you know that PFR, we simply determine the area under the curve. So how to do that? You have to do this numerical method, which you will learn in our previous class. Yeah. So this is mentioned in slide 73. Use numerical method to solve for PFR volume. All right. So this slide is basically showing you an illustration of if you were to determine the volume for each of the three reactors, this is how you should imagine. Okay, the first one simply X times Y, the second one simply X times Y because CSR, CSR. The third one since PFR, then yang ni baru you guna numerical method. Alright? Because kita nak cari area dekat part ni, maybe you can determine the first part here sampai sini because it's the rectangular. But how are you going to find the area here? So that is why you can determine an overall area under the curve by using the numerical method. Alright, so this is an illustration of how you write the formula. So the first formula, the yellow shaded area for the reactor number 1, which is the volume formula for CSER. CSER. The second one would be the volume formula for the CSER again. Alright, since we designed it as such. And the third one is the formula for the PFR. So this is what I'm going to test you today in Kahoot. Yeah, a very simple one. So please take note. Yeah, a very simple one. Should be very easy. Do you have any question before I proceed? Mashita? Okay. Okay, nampak you sebut okay. Amira? Okay. Dia pun sebut okay. Syafiqah? Okay. Okay, thank you Syafiqah. Yang lain tu tak buka kamera, saya tak nampak lah. Buka lah kamera. Okay, now. So we're gonna go to S1. Okay, S1? Alright. Hanani, okay? Nada, okay? Nada, kenapa lah sampai pegang dahi macam tu? Susah ke?
Okey je.
Okay je. Afsar, okay? Afsar, student tak datang ke hari ni? Kelaya kosong? Sekolah tutup ke hari ni? PKP? Cikgu seorang je datang, anak murid tak datang. Macam ni. Rupanya cikgu pergi kelas. Umaira, okay. Anis, okay. Okay. Alright, so now we're going to proceed with the combination of PFR and CSCR. Now we're going to try to look into one CSCR, one PFR, one CSCR. Yeah. Again, a combination, but we look into a mixture of CSCR and PFR, but the arrangement is different, yeah, from the earlier one. The first one was CSCR, CSCR, PFR. Now CSCR, PFR, CSCR. So the isomerization of butane is used as an example. In example 2.7, you can have a look at your textbook, and it's assumed to be an adiabatic liquid phase reactor system. Then I simply make that color coding, inlet for blue, then outlet for green. Yeah, so we have the raw data for varying X from 0 to 65% with the rate of reaction respectively shown, yeah, in kilomole per meter cube hour. All right, so you see that from first reactor, only 20% is achieved in CSCR. The second reactor, PFR, then it increases up to 60%. Then we want to increase it a little bit more, because this is as far that we can increase 65% only by using PFR. Then to increase it a little bit more, we can use CSCR. In this case, it uses CSCR to an additional 5%, yeah, giving you the final conversion of 65%. So let's have a look on the volume determination. So we want to compare how efficient or how good is this design in terms of volume, for example. So you use the first formula in blue shaded area for volume of CSCR. Then the second formula in yellow shaded area for the volume of PFR. Yeah. So it starts with the X1 to X2. Yeah. X1 to X2 there. Then we use the CSR volume again for the third CSR, where the X3 minus the X2, yeah, for that radian, yeah, times the initial molar flow rate from the before the first reactor divides by the rate of reaction in the reactor number 3. Okay, so I'm going to go to the next slide. So of course, we have this illustration just to show you, having that data, it will give you an ascending trend. Then of course, we have X1 there, then X2 there, then X3 there. We're gonna have a closer look in the next slide. This is just predicted, yeah, predicting based on our understanding. But the real trend, since this is an adiabatic, we have that descending trend first, then only increasing trend, yeah, of the X versus FA naught over minus RA. So how do we plot this? So we took it from this data, E27.1, yeah, the raw data for an adiabatic liquid phase reactor. So since we know the first one achieved up till 0.2, so you may take this shaded area to represent the volume for CSER. Then second reactor starts with 0.2 to 0.6, all right? So since this is PFR, so you may take the ruling of area under the curve, yeah, for the second reactor. And the third reactor, since it starts from 60% to 65%, and it is CSCR, so therefore you may take that blue shaded area as to represent the volume for the third CSCR, yeah? Okay, and it is shown there, the first reactor is 188 cubic decimeter, the second reactor 380, the third reactor is 100. So you can see that also in the next slide, slide 80. The first one is 188, the second one is 380, the third one is 100. And this is taken from figure E272, Levenspeed plot for adiabatic reactors in series. You can refer this in detail from your example 2.7, yeah, in your textbook. Yeah, Akasha. Akasha, okay?
Okay, Doctor.
All right. So now we'll go to the next slide, yeah? The questions would be, what is the best sequencing? Either CSCR or PFR first. In other words, it means which goes first to the highest overall conversion, right? So let's have a look at this comparison, yeah? If we were to compare the first reaction, the first reactor type to achieve the same conversion, yeah, from 0 to 0.2. Remember, we did that for 0 to 0.2, yeah, for the first reactor. And this one on slide 80, we tried it with the CSCR as the first reactor. If we were to compare, why not if we try PFR as the first reactor instead? To achieve the same conversion, which is 0.2. So logically, if you know that to determine the volume, if you were to compare based on volume, then for PFR, definitely we have to add another additional area there, right? For CSCR, we just need that shaded area. So therefore, you know the total yellow shaded area is way bigger than the blue shaded area. All right, do you have any question here? So we can say that the volume for the CSCR is lower than the volume for the PFR. Okay, do you have any question there? That is our first conclusion. If you were to compare between two type of reactors in volume, in the sense of volume, then you may say we need more volume, higher volume if we use PFR rather than CSER. All right? With that range of conversion. Okay, gonna go to our next slide, slide 82. Now, for this condition, again, adiabatic condition for a starting of 0.2 to 0.6. So again, this is a series, yeah? If you were to use PFR as our second reactor, then you take note that the area, the additional area up there are needed, yeah? Giving you the conclusion that, again, the volume for the CSCR is lower than the volume for PFR needed if we were to use that for the second reactor for this series configuration. All right. Then we go to the next one. The third reactor, we earlier chose PFR. Now, if we were to choose PFR, CSCR from 0.6 to 0.65, so you can say that the volume for CSCR now is greater than the volume for PFR needed for the third reactor for that range of conversion. Okay, Mashita? Najwa, okay.
Okay, Doktor.
All right. So, I'm going to proceed with part 3. If you have no questions, you have any questions? Okay. So this is part 3, reversible reaction for an autocatalytic, and also we will also cover on autocatalytic reaction, yeah, after that. Let us start with the reversible reaction. And this is taken from our previous slide. We know that for an elementary equation, and you write the rate of reaction as such, yeah, for that example of reaction. Okay. And for a reversible reaction, we have a forward specific rate constant Kb, and reverse. If you were to write it with respect to B here. B here means I simply write that as B, yeah, because from our previous slide we used that B, yeah. No, this is not the same as the previous slide. This is simply a different equation, but I simply choose 2B, 2 moles of B produces 1 mole of D, produces 1 mole of hydrogen. So the D represents diphenyl, B represents benzene, all right? 2 moles of benzene produces 1 mole of diphenyl and 1 mole of hydrogen. So we write the rate constant, the K, with respect to B, and that B is with respect to your raw, reactant, yeah? And since this is a reversible reaction, so take note, the reactant, if you go forward, if the reaction goes forward, then the reactant is benzene. But then if it goes back in reverse direction, then your reactant would be diphenyl and hydrogen. I hope you understand that, right? For a reversible reaction. So in this case, for the K, the rate constant, we write based on, or in other words, with respect to benzene as your reactant. Yeah. So that is why when in an opposite direction to the left with respect to B still, so we use K with respect to B since it is an opposite direction, so we add this minus sign, yeah, K minus B. All right, this is just to refresh what we have learned so far in week 3. So that was done in week 3. Now, so this is again from our previous slide in week 3. Take note of how we write the rate of disappearance, the forward reaction, yeah, the forward. So another word that we use here, forward, yeah. So if the rate of disappearance of the benzene forward, then simply Kb times, this is elementary, Cb, the concentration of benzene squared because we have 2 moles, all right? So for the reverse, why we make it, we bring the negative sign to the right, because if you go to the next slide, we want to add that to the net rate of formation of benzene. Yeah, it's simply the RB forward plus RB reverse. So without the negative sign there. So if you go back to our previous slide, so that is why this equation is purposely written. Yeah, so that you could substitute that in the net rate of formation equation. So for the rate of formation in a reverse reaction, you do the same thing. Yeah, but now we use the K minus B. Since it's reverse, so the reactant now is the diphenyl and hydrogen. So we have CD to the power of 1 mole of diphenyl, and C concentration of hydrogen to the power of 1 since 1 mole of hydrogen. Okay. So simply add that, substitute those 2 equations there, then you'll get your net rate of formation equation. Now we're gonna look into the reversible reaction, this time in topic 5, to another term, which is the capital K, which we call it as equilibrium constant. Before that, we only have the forward rate constant and the reverse rate constant. All right. So those are the equations that you refer to when you write your rate constant or the rate of reaction equation. Then if we are now going to define the equilibrium constant, which means the forward specific rate reaction rate constant divides by the reverse. So simply the Ka divides by the K minus A. And now here we write it in terms of A. Yeah? A here is according to this formula, this reaction formula, which is the reactant A that we have here. So this K is written with respect to reactant A, right? So please take note. If you go back to our previous slide, of course, we wrote it based on the reactant also, but since we use B, then we write it with respect to benzene. So it depends on how you write your formula. Yeah. So what you need to understand is you write your rate constant with respect to which reactant. Itu je yang penting kena tahu. So in an equilibrium, in a reversible reaction, so what happens in there? Yeah. At equilibrium, for this reaction, since this is, okay, let's say it's an equilibrium, a reversible reaction, the concentration are related to the thermodynamics relationship for the equilibrium constant. Yeah. At equilibrium, the reaction rate is 0 for all species. So this is what happens during equilibrium, which means the rate of formation of a particular species is defined as such. Yeah. The R forward plus the R reverse. So this is how you write the whole thing for the equation of K, capital K, the equilibrium constant. Since we know that the equilibrium constant is as that ratio formula for the rate constant with respect to A, now we are going to write the equation for the rate of reaction with respect to A simply by writing, since it's a reversible reaction, so you write based on the net rate of formation, yeah? So simply adding the R forward plus R reverse, rearrange it so that we can write it with the K, the rate constant with respect to A. Then you have this ratio, and that ratio is simply the reciprocal of the equilibrium constant, yeah? So the overall formula for the rate of reaction with respect to A for this reversible reaction is written by the shaded, yellow shaded area formula. Now you have it in the function of K, all the C's, and also the equilibrium constant. All right? Okay. Do you have any question before we proceed? Afsar? Dia tanya nama orang lain pula. Azri? Mana Azri? Mirza? Kamilia? Anis? Syafiq? Mana Syafiq? Najwa? Mana Najwa? Najwa ada. Sorry Najwa. Azri mana Azri? Selalu saya tengok kelas, kadang ada kelas tu bila saya dah habis, when I finish my class, tengok je ada lagi yang tinggal duduk je kat situ. Tak tahulah dia nama je kot kat situ, but that particular person is somewhere else. Tahulah kat tandas ke, baring kejap kat katil ke, atau tertidur berdengkur sampai tak sedar. Mana tahu kan? Kalau saya take a break 5 minutes break, saya tidur berdengkur, tak masuk-masuk tu, maksudnya berdengkur lah tu. Okay, Syafiq ni Syafiq. Azri mana Azri? Atrisha mana Atrisha? Ha? Tak ada. Ada ke ni kamu dalam kelas? Ada ke ni? Azri. Nak panggil lah. Dalam kelas macam pelik lah pula. Kalau face to face, semua ada depan saya kena panggil Azri. Tidur ke? Azri. Syafiq. Tidur Bagusnya pensyarah lembut-lembut cakap. Dalam kelas pun Azri tidur Awak rotan ke baru tahu? Mana Azri? Nak rotan? Syafiq. Azwan tengah duk hantar WhatsApp tu. Bangun. Korang bangun. Pensyarah panggil. Nampak Azwan hantar WhatsApp. Tengok tu. Lagi tak ada, saya tak go forward. Cepat Azwan. Mana Azri dengan Syafiq? Spot check. Nak raya ni pun bulan Ramadan ni.
Azri ada cakap dekat chat doktor.
Oh, ada kat chat. Oh, ya Allah, Tuhan, kesian dia. Thank you. Azri, saya madam, internet saya slow, kesian. Okay. Mikrofon tak boleh buka ke, Azri? Mikrofon. Kalau buka mikrofon ni ganggu internet. Tak ada jawapan. Syafiq? Sekejap ya. Macam tu lah.
Hello, test.
Test. Macam baru nak test je sebanyak 5 minggu.
Tak ada. Internet lambat hari ni.
Okay. Dengar suara. Nak dengar suara Syafiq pula. Mana Syafiq? Cepat Izwan. Cari Syafiq, mana Syafiq? Tak dengar suara. Tak tahu, saya tak nak go forward.
Hello.
Alhamdulillah.
Doktor Syafiq mana?
Ha? Sorry, Patricia. Okay. Tak boleh buka cam. Tadi Syafiq ke?
Syafiq ada dua, madam.
Oh, Syafiq ada
Doktor
dua.
mencari Syafiq yang mana?
Mana-mana lah jawab Syafiq pun. Cover line lah. Boleh
Oh,
kamu. Kan
okey.
saya dah
Saya
tahu dua
ada.
Syafiq. Kan saya dah tahu dua Syafiq. Boleh kamu ni. Cover line pun tak tahu.
Oh, saya ingat kan doktor tunggu Syafiq yang satu lagi.
Manalah saya tahu ada dua Syafiq ke? Muhammad Syafiq. Ada lagi satu Syafiq.
Saya. Saya Muhammad Syafiq juga.
Muhammad Syafiq. Dua-dua Muhammad Syafiq ke?
Kebetulan.
Apalah. Cover line tak kerti. Jawab je lah.
Syafiq satu lagi ni manalah.
Kan dah kata lagi seorang tak ada. Okay, kita panggil dia kemudian. So let's proceed, alright? So we're going to go to our next slide. So you can see that on this slide number 92, so we have exothermic, we have endothermic. So we are talking about the equilibrium constant Kc. So take note of the capital K. The equilibrium constant for the exothermic decreases with the increasing temperature, and the equilibrium constant for the endothermic increases with the increasing temperature. Yeah, so you can refer to this. And when we talk about reversible and non-reversible or irreversible, basically for any reaction, we know that through time the concentration of the reactant will decrease, and at the same time the concentration of the product will increase. You know that, right? But in an equilibrium, the forward and the reverse will meet up, yeah, at certain time, yeah, according to the reaction rate. So that would both would represent the happening in any reaction, but the right hand side is representing in terms of the reaction rate according to time. So until certain time, the forward and reverse will meet up, meaning it will reach its equilibrium state, yeah, at that particular time. All right. And this slide 94 shows on how we write the equilibrium constant. Yeah, the first one is based on the Kc, which is the concentration. The C here refers to concentration. Then the P here refers to pressure. Yeah, so we write it as pressure equilibrium constant, and Kc is concentration equilibrium constant. And you know that for any gas phase condition, the concentration of the gas is actually the partial pressure. So if you are dealing with a gas condition, then you may write the equilibrium constant based on pressure, which represent the concentration of the gas itself. Yeah, we'll still write based on K forward and K reverse. Doesn't matter if it's concentration equilibrium constant or pressure equilibrium constant. But the equation here is what you wrote earlier for the forward reaction and the reverse reaction respectively. Here we have the notation E here to represent, just to make it, just to allow the reader understands that we write the concentration of the C here is the reactant, C here is the component, to the power of C, and E here refers to equilibrium. It means the concentration of C at equilibrium, and CDE is the concentration of D at equilibrium. Yeah, same goes to the partial pressure of C at equilibrium and partial pressure of D at equilibrium. All right. So now we're going to enter to the last part of this part 3, which is autocatalytic reaction. So what does it mean by autocatalytic? We know that in any reaction, we may have catalysts. And in this case, the example of decomposition of the C2H4I2I 1,2 diiodoethane, either in gas phase, it simply decomposes, and or it decomposes in carbon tetrachloride solution. Yeah. Other example would be the hydrolysis of ester or some other microbial fermentation reactions whereby some of the products are the catalysts for the reaction. In this case, if you see from the figure, we have two kinds of curve. The first one and the second one. The first one has no R in fit, meaning we are talking about A decomposes to product, and that product is written as R, and that R is used when it's increasing, once it increases through time, and that R is also used for the reaction. Yeah. So those two curves are shown for the first one, where we have an initial speed of the R already, but the second one has no initial R. Yeah, simply depends on the R produced. All right, so that is just to differentiate between those two curves here. So it's written here as the rate at the start is low. Of course, when we start any reaction, the rate of reaction will be as low as possible. Yeah, it starts from 0. Then at CA0, yeah, with that low concentration, with that certain concentration of A initial, because the product is low. Yeah, product is the catalyst. In this case, that's why we call it as autocatalytic reaction, because it depends on the product as the catalyst to speed up the reaction. As the rate starts to increase, yeah, as the product increases to a maximum product formation. So that is why we have this blue shaded area, and also that blue shaded area. The lower one is for the second curve, the higher one is for the first curve, yeah, with the initial R in feet. Yeah, this is just to say that the rate of reaction increases, yeah, from CA0 to a certain C. Yeah, as time increases, CA will decrease. So that is why for the x-axis, the CA0 starts from your right, because CA0 is bigger than your CA at any time. All right. So for this one also, you can see that the rate of reaction increases. So let us go to the first one, whereby we have no R there. So you can see that the rate of reaction increases when CA, yeah, CA0 goes to your left. Of course, through time, time increases, then the concentration of the A decreases. Yeah, so it reaches at certain point. Yeah, the rate of reaction reaches at certain point, and also at certain when it reached that level, yeah, of course, the rate of reaction becomes 0. Yeah, all right. So that is the minimum point there for that curve, for that peak. All right, and at that specific P here, P minimum. P here refers to the product. The rate at the start is low at CA0 because the product is low, and the rate starts to increase as the product increases to a maximum product formation. So we have P max here, whereby the product reaches its maximum yield or production. All right. Now, this is for no R in fit, and this is for some fit in R. The same thing, it increases until it reaches its maximum product formation. Yeah, maximum product formation there at that point. And also the rate of reaction also reaches its maximum point there. I would go back here. I think I remember I said it reaches rate of reaction 0 here. I'm so sorry there. That would refer if we were to get the DRA over DCA. Yeah? So that would mean 0 for that point. This one is simply means when you start. So I would rephrase that. Yeah, I think I said it wrongly earlier. Yeah. My mind was referring to the curve where the peak, you know, mathematically, if we get the dy over dx for x and y for that peak, then it will give you a value of 0. Yeah, don't get confused on what I said just now. Yeah, so I take it back. So I try to correct it. All right. So then after that maximum level of the product formation, the rate of reaction starts to decrease. Yeah. Says that the rate starts to decrease, drops again as the reactant decreases, consumed, whereby you have the reactant now being used by the reaction, and as the reactant, as the product which we say as reacts as the catalyst now being consumed during the reaction. So that is why the rate of reaction starts to drop. Yeah, in this case, decreasing through time. All right. Same goes to the other condition. It also starts to decrease or to drop. So this is a summary of the overall occurrence during this autocatalytic reaction, whereby the rate of reaction increases to some point where until it reaches the maximum product formation. Same goes to here, to maximum production. All right, then it starts to decrease to a certain point as well. Yeah, so this is a plot for the rate of reaction versus the concentration. If you were to plot of the reciprocal of the rate of reaction versus the conversion. So now we're going to look into the conversion. Yeah. If you look at this slide, we compare between plug flow and also mixed flow. Yeah. The question would be which reactor would be better or superior. All right. So if you look into the three comparative figures for the reciprocal of the rate of reaction versus the x. So why do we do that? Do you have any answer? Why do we make this comparison whereby the y is now the reciprocal of the rate of reaction? If you look before, we only analyze based on the rate of reaction, but now why we want to compare based on the reciprocal of the rate of reaction? Do you have any answer? Kenapa? Kenapa tiba-tiba nak compare pula satu over rate of reaction? Tadi duk seronok-seronok rate of reaction, tiba-tiba nak buat 1 over RA pula. Kenapa? Why? Hanani? Hanani?
Saya pun tak tahu.
Tak tahu? Najwa lah, Najwa macam ada jawapan je. Kenapa tiba-tiba nak buat reciprocal pula ya?
Tak tahu doktor.
Tak tahu juga. Takkan dengar je saya mengajar tapi tak tahu. Afsar?
Nak jadikan dia supaya graf sama untuk kira volume tadi. Volume
Pandai. Pandai pun Afsar. So kita pergi balik kepada kita punya slide sebelum-sebelum tu ya. So when we want to determine the volume ya. So we know that our rate, the volume equation, tengok kat sini. for CSER, slide 78 ya. So you have 1 over RA compare dengan X. Even for the PFR pun 1 over RA compare dengan X. Betul? So this is what we have been doing so far. The y-axis is the reciprocal of the RA comparison to the X. So that is why when we want to analyze based on that problem statement, which would be superior, yeah, for this autocatalytic reaction, regardless of the molar flow rate initial, regardless, tak kisahlah, molar flow rate initial tetap sama kan. So nanti kalau you nak compare pun, this is just generally to answer that question, yeah. So later on, once you know that your molar flow rate is simply multiplication je lah kan. Ni hanya nak jawab soalan basic saja. Which reactor is better or superior? So if you look at the, let's say if we have A, B, C there, so we know that from our previous slide for this autocatalytic reaction, if you were to plot 1 over RA, then it becomes an upside down curve, betul? So this is what you see for that condition. Yeah. So we have, let's say if you choose mixed flow, then simply you take that area, yeah, for mixed flow from 0 to XA here until that point. If you extend it to that point, mixed flow, the shaded area or CSCR here, katakan CSCR lah. Then the plug flow yang dot tu sampai the whole thing, yeah. So if I change my, let me change my highlighter to blue. So the plug flow is that. That is plug flow area. All right. For the third one, see, the plug flow area is that. If you were to compare between 0 to until that final conversion, yeah, and the CSCR area is this whole thing. In that case, would give you an approximate overview of which reactor would be much superior. Yeah. So what can you say? What can you say? So we compare between 3 conditions for this autocatalytic trend. The first one is from 0 to that level. The second one is from 0 to that level. The third one is from 0 till the end. Sampai sini. All right, so we're going to go to one by one in the next slide. If you were to compare the conversion from 0 to that level of final conversion, then the CSCR area would be that area which is lower than the plug flow area, right? The plug flow area is way bigger, yeah? As shown by the purple color, by this purple highlighter, purple, right? All right, so we can say the mixed flow is better in terms of volume. All right. If you go to the next higher level of conversion from 0 to that point, then the left hand side is the PFR, the right hand side is the CSCR. So what can you say? It looks like approximately, so nampak kat sini ya, that small portion might be the same as that small portion there. So we can approximately say the mix and plug flow are equally good, yeah, in this case. If you go to the next level whereby you want to compare between 0 to an even higher level of the conversion, the left hand side will give you the area for the PFR. The right hand side shows you the area for the plug flow, for the CSCR. And you know the volume for the CSER is way higher in comparison to the PFR. So we can say the plug flow is better in this case. So the final conclusion would be the mixed flow reactor is superior than PFR if we have low X. If you go towards higher X, then high X PFR is better because the volume needed is lower than needed for CSER. Okay. And now the last part will be that this will be the last part, yeah. Just to show you the application of deciding whether you want to go for CSER or PFR. In this case, it gives you a conclusion saying that I'll just go forward with the conclusion. The impact of recycling is minimal volume is operated. Yeah. Meaning in this case, if we were to use that as a recycling tank, then the mixed flow is chosen. Yeah. So in this case, what happens is that we have CSER with an initial concentration of A. The outlet from the CSER is fed to another mixed flow reactor or separator or recycling tank, so that you can take out your final product and recycle your unused reactant back to the CSER. Yeah. So one step with the use of the mixed flow reactor in a single reactor, meaning this whole thing like a whole set whereby we have the CSER with the recycling stream. Yeah. So we have the CSER with the recycling stream. Still get the same trend there, achieving a certain optimum level of the concentration of the A for this set of reaction, yeah, with the CSER and also the recycling tank. So let's say if we were to compare between the CSER and also the plug flow reactor, so we have here the CA naught. Of course, if you compare the CA versus the reciprocal of the rate of reaction, the CA is definitely higher. So it starts from here. So the curve starts from left to right. Yeah. So we have this mixed flow reactor, which is the CSER with that volume, and you continue with the PFR with that specific volume. All right. So in conclusion, it says that when we have this combination of reactors, CSER and also PFR, it represents as if we have one set of reactor of this CSER with the recycling flow. Yeah, that is just to show theoretically that if we have one CSER with the recycling flow, it behaves like the combination of CSER together with the plug flow reactor. Okay, so that would be the end of the topic 5 chapter. But before we end, I just want to end this with the last part of the autocatalytic reaction, whereby you have PFR as an ideal recycle reactor. It says there, for the end order of reaction greater than 0, the plug flow reactor is always more efficient than the mixed flow reactor. And however, the PFR will not operate with a feed of pure reactant, which therefore PFR is suitable for using as a recycle reactor. So this is what happens here, whereby we have this PFR which behaves like this set of combination CSER, and then the PFR principle is applied for this recycling stream. Yeah, meaning since the PFR type is not suitable for receiving pure reactant. So that is why it is used for this set of reaction with this main reactor with a recycling stream. Okay, so that will be the end of this topic 5. And we will take our first 5 minutes for our next activity. All right? Okay, tunggu ya, 5 minutes break.